From solving problems involving tiny particles to studying bizarre phenomena like space-time interactions. This field continues to evolve, surpassing all limits we have ever known. If scientists can verify the accuracy of this latest discovery, after firing tiny electron particles through a 15-meter diameter ring at the U.S. Department of Energy's Fermilab in Batavia, Illinois, scientists have measured quantum fluctuations in neutrinos, a phenomenon that cannot be explained by the standard model of particle physics. This could imply the existence of a fifth fundamental force in nature that humans have yet to discover. The muon is a stable particle with a negative electric charge, similar to its close relative, the electron, but it is about 200 times heavier. Meteor showers form naturally when small meteoroids collide with Earth's atmosphere. The important thing is that these particles also have quantum properties and oscillate as they move within a strong interaction field. These new findings reinforce the previous discoveries from 2021 but are built on a dataset 4 times larger for analysis. Thus, they further reinforce the claim of a new branch of physics. Scientists at Fermilab have published the details of their research in a scientific paper submitted to the journal Physical Review Letters. According to a hypothetical study by Brandon Casey, a senior scientist at Fermilab, we are trying to find clues to determine whether the WASP is in contact with something mysterious that we have never known before. It could be anything: a new particle, a new force, another dimension, an unknown property of space-time, or anything else. Casey hypothesized that these results might hint at a new property of space-time or a violation of Lorentz invariance. A principle asserts that all physical laws remain unchanged regardless of location. He said it would be a crazy and highly challenging endeavor. For centuries, scientists have tirelessly worked to unravel the phenomena at the subatomic level, where particles smaller than atoms exist. The atom is the fundamental unit of matter that we can see and touch. Atoms often bond together to form molecules, which in turn make up solids, liquids, and gases. Physicists use a theory to describe how the universe operates at the subatomic level. The Standard Model was developed in the early 1970s. This theory posits that all matter in the universe is composed of a small number of fundamental components, called elementary particles. For their part, these particles are subject to 4 fundamental forces: the strong force, the weak force, the electromagnetic force, and the gravitational force. In the 20th century, the Standard Model evolved into a robust physical theory, rigorously tested and capable of accurately predicting various phenomena. However, this model cannot explain some of the deepest mysteries of modern physics, including what dark matter is composed of and the disparity between matter and antimatter in the universe. To unravel these mysteries, scientists have been searching for particles with properties distinct from those of known particles in the Standard Model. Recent experiments at Fermilab, called muon G2, have studied the wobble of muon particles as they move through a magnetic field. Like the electron, the muon also has a tiny internal magnet that causes it to wobble, or in technical terms, undergo precession, much like the axis of a spinning top. The Fermilab experiment was conducted under extremely low temperatures, reaching down to -268 degrees Celsius. The muons were fired into a superconducting magnetic ring, which appears to be a semiconductor with a diameter of 15 meters. The muons travel thousands of laps in a circle at nearly the speed of light. The scientists are striving to measure how they oscillate. When muons move in a circular orbit, they interact with other subatomic particles. These particles are like tiny dancers, altering the oscillation rhythm of the muon particles. The machines arranged along the circle help scientists measure the precession speed of muon particles. According to the muon magnetic moment theory, the measured energy value of a particle when aligned with the magnetic field must be slightly greater than 2. However, newly published measurements show that the muon particle's magnetic moment is stronger by about 0.2 parts per billion, a small but significant difference. Currently, the research team is continuing to work on collecting additional data over the next 3 years to obtain more accurate measurements of the muon's magnetic moment. In short, these new findings continue to suggest the existence of certain mysterious elements, possibly unknown particles or forces, and is as significant as the discovery of the Higgs boson in 2012. In the early universe, time passed 5 times slower than it does today. Astronomers have peered back to the dawn of the universe and discovered that time flowed 5 times slower back then compared to today. Finally, they proved the prediction made by Albert Einstein over 100 years ago. Scientists have discovered an extremely slow motion effect when analyzing data from extremely distant and ultra-bright celestial objects, also known as quasars. According to Professor Jerry Lewis, an astrophysicist from the University of Sydney, when the universe was just about 1 billion years old. When observing the universe at just over 1 billion years old, we notice that time appears to flow 5 times slower than it does today. If you stood there, in that early universe, 1 second would still pass just like a second. But from our present-day perspective, more than 12 billion years later, that ancient time appears to have passed more slowly. The reason why time felt like it passed more slowly in the early stages of the universe. From the perspective of modern researchers, this is the first time the phenomenon was mentioned by Stauncking in his broad path theory in 1915. Because the universe is expanding at an increasingly faster rate, the light emitted from a distant source is stretched, causing its wavelength to become longer and redder. More importantly, the interval between light pulses was also extended to 5 times the original length, making time seem to stretch and slow down. Lewis Wright and many scientists like Stauncking have proven that time and space are closely interconnected. The universe has been expanding continuously since its inception, the Big Bang, the first singularity of spacetime. The expansion of space means that our observations of the early universe appear to unfold much more slowly compared to the present timeline. Black holes form from the collapse of massive stars and continue to grow by absorbing gas, dust, stars, and other black holes into themselves. For certain ravenous spacetime rupture points, when friction heats up matter, it emits light that telescopes can observe, turning black holes into what are called active galactic nuclei, or AGN for short. AGN, particularly quasars, are essentially supermassive black holes with masses billions of times that of the Sun, in the process of shedding their outer layers. When the explosions occurred, they emitted light thousands of trillions of times brighter than the brightest stars. However, interpreting their complex light rays remains no small challenge. Therefore, until now, instead of studying light, astronomers have primarily focused on the evolution of massive cosmic explosions such as supernovae. To explore the timeline in the early stages of the universe, Lewis explained that, unlike supernovae which act as a single beam of light, a characteristic that makes studying them easier. As quasars grow more complex, they resemble a dazzling fireworks display endlessly shooting into the sky. We have decoded this fireworks display, proving that quasars can also be utilized, marking the standard timeline for the early universe. To detect this effect, astronomers analyzed data from 190 quasars collected over 20 years, and analyzed the different wavelengths emitted to calibrate their standard brightness. Thus, they become the ticking rhythm of the universe's clock. Previously, time dilation has been observed in slower-moving supernovae, at around half the current age of the universe. But tracing back to a time when the universe was only a tenth of its current age has been confirmed. This effect occurs at all levels of the universe and becomes increasingly evident as distance grows. This also refutes previous studies on quasars, which did not detect this effect. Lewis shared that previous studies had left people inevitably puzzled. Is a quasar truly a cosmic object, or is even the idea of space expansion accurate? However, thanks to new data sources and analysis, we have been able to detect faint, elusive signals from quasars. And they operate exactly as predicted by Einstein's theory of relativity. NASA's rover has discovered a strangely shaped rock on the surface of Mars, on the journey to explore the Zero crater in the northern hemisphere of Mars. NASA's Perseverance rover has discovered a uniquely shaped rock that looks just like a donut. The rock was photographed from a distance of 100 meters using SARMA's microscopic camera. On June 22, 2023, a component of the SuperCam instrument on the rover was documented. Day 832 on Mars in the journey of space exploration. On Mars, rocks with strange shapes are a common feature. They could be the result of prolonged erosion, similar to the phenomenon that occurs on Earth. However, the conditions on Mars do not allow for erosion by water to occur. This indicates that wind and sandstorms are the main agents causing weathering in this area. Mars has a year nearly twice as long as Earth's. The red planet will endure fierce storms. Every few years, this phenomenon coincides with the southern hemisphere's summer. Mars is experiencing a massive dust storm, which could engulf the entire planet and last for months. Like the sugar-coated donut-shaped rock discovered by NASA's Opportunity rover in January 2014. This newly discovered rock may have formed after one or more smaller rocks eroded near its center. The photo also shows smaller rocks of similar colors scattered around. It can be seen that they share a common origin. Over the years, autonomous rovers such as Curiosity, Spirit, and Overture NRT have operated together. Fragments from meteorite collisions have been discovered on the surface of Mars. Thanks to Mars' thin atmosphere, meteorites often leave more debris on the surface, and impact craters are also better preserved due to the absence of rain. Starting February 18, 2021, the Perseverance rover will begin operations on Mars and continue exploring the Jezero crater, once an ancient lake. The vehicle is busy collecting samples from the fan-shaped delta, which shows traces of flowing water and sediments that once poured into the crater. These samples will be collected through the MAX SAMPO return mission. NASA and ESA jointly launched an orbiter along with the lander. The compact Earth Sand rocket along with VICO and 2 helicopters. Analyzing these samples will help clarify the geological and environmental evolution on Mars, as well as the potential for past life to have existed there.